Hi, welcome back. We've so far spoken about the contrast between Newton's laws of elasticity and viscosity, the idea of viscous and elastic properties, Newtonian and non-Newtonian behavior. And now we're going to turn our attention to a little bit more detailed view of water at the level of many molecules. So this is the sort of cause for this heading, which is the molecular nature of water. What we're going to talk about now is to see if we can put what we know about the shape and structure of water into the context of its physical properties, and finally do what I have been promising so far, which is relate it back to the biological relevance of this. So if we go back and look at our classic view of the molecule that is water, it is indeed, as everyone with a basic high school education knows, H2O, where two hydrogen atoms bind to one oxygen atom. The structure of water is interesting because, as you see here, there is a central oxygen, which we say has a sort of charge which is twice delta, right? Negative. And there is a perhaps balancing charge of small delta positive on the hydrogen, right? And since there are two of them, there's delta minus, delta plus plus, and delta to delta minus. The angle formed between these two at the vertex of that oxygen is indeed the 104.45, and the vertex, of course, being defined by oxygen. The length of the bond OH is found to be 0.97 angstroms. And this allows us to now think of water as a sort of geometric object, right? This is in contrast to what you traditionally read in the context of water in terms of the chemistry. I may even add stereochemistry. Now, charge. Okay. And we'll see that this approach has some advantages. Just to remind you, 1 angstrom is nothing but 10 to the power minus 1 nanometers. Yeah, it's important because in biology we often use angstroms because it's a convenient measure at a molecular scale or atomic scale. But SI units mean that it's meters. Meters is 10 to the power minus 10 meters for 1 angstrom. Or in other words, 1 nanometer is equal to 10 to the power minus 9 meters. Yeah. So why is water so special, right? What makes water special? We're going to first talk about what this is in terms of the physical chemistry of it, the physico-chemical properties. And then we'll try to see if that allows us to answer the question, for biology, what makes it special, right? So we are aware of the boiling point is 100 degrees Celsius at 1 atmosphere. That is to say 101.3 kilopascal. The freezing point is a triple point. The viscosity has unusual properties that arise out of a hydrogen bonding network. There is cohesion, which leads to things like surface tension, allowing, if you remember, on a static body of water, certain kinds of insects to walk on it. Water striding insects. And we won't have time to discuss it, but these are all due to surface tension. The triple point of water that I mentioned earlier allows us to observe that if we play around with temperature, pressure conditions, that water can coexist at the same point in PVT space, that is pressure, volume, temperature space, as a solid, a liquid, and a gas. This makes it very unusual. I don't know if you realize this, but you think of any other liquid which coexists as a solid, liquid, and gas at the same time. Think about ethanol. This is what is in the drinks that some people drink, or think about petrol, or think about what other fluid do you want to think about? Ammonia, the gas, or you think about oxygen. Does it exist as a solid, liquid, and vapor at the same time? I mean, you don't find this, right? And there are interesting volumetric anomalies. There is a glassy state, and this coexistence makes all of these make water to be an unusual fluid. Indeed, anything we say about water in terms of being special is with relation to other fluids. So here is an example of the temperature dependent state changes in the freezing and boiling points, meaning to say the temperature below which that fluid will become a solid and above which it will become a vapor or gas. What you should notice is that our favorite fluid, namely water, right, has a freezing point higher than all others, boiling point higher than all others, and critical point higher than all others. And by others, we mean methane, ammonia, water, hydrogen fluoride, and neon. And there is a lot of work on the prebiotic life that has asked the question whether in the prebiotic soup, why is water the preferred solvent? And in order to answer some of these questions, and we're not going to be able to answer them, you actually need to go back and look at the geochemistry of prebiotic earth. And this is a topic unto itself. I think for those who are interested in this, you should actually go and listen to lectures on the origin of life on earth and so-called chemical evolution of life and the biological chemistry of it. Okay. Suffice to say that this is sort of the triple point that I was mentioning in terms of temperature, pressure, phase diagram of water, where a transition between gaseous, solid, and liquid phases exists with these critical points marked that lead to transitions between the three states in the lower case at the triple point and a critical point of transition from gas lower into liquid. Right, and these terms, sublimation, deposition, freezing, melting, also tell you that you can go, in the case of water, from gas to solid directly. So basically go from water vapor into ice or snow. And I'm sorry, that is deposition. And from ice or snow to go straight into water vapor, that is sublimation. And melting, freezing, you're familiar with. Vaporization and condensation, you're also familiar with. So this is sort of a very nice reminder that water has amazing physical properties and the chemistry that is related to it helps us understand it, but we want to know what the consequences of the special properties of water are for cells. One example is what happens when we do cell culture. And those of you who have ever grown bacteria or fungi or mammalian cells, and this diagram summarizes how, for example, mammalian epithelial fibroblast cells in an adhered form can be stored for long-term use storage in a frozen state. So the idea is that they are growing in a petri dish, in a culture dish. The cells are submerged in growth medium, and you need to detach them. Typically, this is done using something called trypsin, which breaks the bonds of the cells to the substrate. They're resuspended in a tube. The tube is centrifuged to get rid of the supernatant, add fresh growth medium along with the cryoprotectant. And this sort of depends, but typically you will find protocols or reproducible methods recommend to you 10% volume by volume of DMSO or glycerol. My first question to you is why? Yeah? Why do we use DMSO or glycerol? Then the next step is cooling down the culture by gently freezing it in a stepwise manner with -20, -80, and followed by -195.8 degrees Celsius in liquid nitrogen vapor phase. So the next question I have is why? Why do we do this process so slowly? And then we store it, right? There's a second step, which is when we actually want to use it, we revive it. And that is rapid, where we thaw it for 1 to 2 minutes at 37 degrees Celsius, for example, with these epithelial cells. And observe till the point that there are no ice crystals, then wash, meaning to say centrifuge, discard the supernatant, replace with growth medium, add fresh culture medium, and grow again. Why is there a difference in the rate of freezing and thawing? And why do we add glycerol or DMSO? Part of the answer to these questions lies in the fact of the structure of molecular water. And the fact that while 75% of the cell mass is indeed made up of ice, or I'm sorry, of water, when we are freezing it, if you allow it to form the normal ice structure, then there's a very good chance you're going to disrupt the cell structure itself, break it in other words. And this comes to viability. So in other words, the freezing and thawing process are crucial to maintain the viability of cryopreservation of cellular material. Cryopreservation is referring to the fact that we preserve these cells at low temperature. Cryo meaning low temperature, cold. So what is the special structure of ice that requires such care, right? And that's what we're going to talk about next. And we're going to talk about this in the context of what I refer to as the statistical redundancy of configurations of molecular water. Hi. So we said this earlier about the structure of water, which consists, I have taken these two pens to represent the two hydrogen bonds, O to H, joined at the center by the oxygen and an angle of approximately 105 degrees between them, 4 point something, right? Uh, this picture is a static picture, right? You are aware that molecules are not always just stationary, especially not in a fluid, right? So they're moving around. And when they move around, they keep interacting with other molecules. I mean, this is just one water molecule. Water as in water, pure water, consists of multiple water molecules. So let's see what that gives us. So it turns out that the standard model of molecular water was proposed in 1892 initially by some very simple ideas about multiple states by Röntgen. Röntgen was the German scientist who also discovered X-rays. I'm sorry, that was 1892. Then 1933, Bernal and Fowler came up with a model of a tetrahedral geometry. So this is a tetrahedron, a geometric tetrahedral object that takes into account what we showed earlier about the molecular structure of water, 104.45 degrees between the HOH, and arranged in a tetrahedron. How in a tetrahedron? Of course, these two angles are not the same. So what are we talking about? So it turns out that water, because of that small negative charge on the oxygen, delta 2 minus if you recall, and the small positive charge, delta plus, on each hydrogen atom, is capable of now creating a hydrogen bonding network. Right? These dashed lines here indicate the fact that there is a weak interaction based on electrostatics between the hydrogen and the oxygen of a neighboring molecule. Now, this would suggest an interesting property, which means that you remember I said that the water molecule can move around because it's in a fluid, but that certain positions are likely to be more favored than others, energetically more favored than others. And this brings us to the question about the statistical redundancy of H2O and its molecular components. So it brings us also forward to 1935. So Bernal-Fowler model of tetrahedral geometry was 1933. This paper, published by Linus Pauling, Nobel laureate in chemistry, and Pete Slater, describes the structure and entropy of ice and other crystals with some randomness of atomic arrangement. Now, this is interesting for two, three reasons. One is that it talks about the structure of ice. Second is talks about entropy. So far, we haven't talked about entropy. You're aware of entropy in other contexts. And it talks about randomness. And this is where my statistical variations business comes in, right? You can read this paper, it's available online. But for me, the most interesting part is that it describes one kind of water being ice, that ice that is found in a freezer if you have one with ice cubes. It is also found in the glaciers. This is the Chota Sigri Glacier of Himachal Pradesh, 4,900 meters above sea level. That water has this structure, right? What you're looking at here. It's also called 1H form. The Bernal-Fowler model that was adopted by Pauling has the following properties. Ice has a distance of 0.95 angstroms between the O and H and an angle of 105 degrees HOH. Each H2O molecule orients two hydrogen atoms towards two oxygen atoms, which is sort of what I showed you in my very crude diagram here, right? We'll get to it a little bit more in detail. Four oxygen atoms tetrahedrally surround a single oxygen atom. We'll see how that works. Adjacent H2O molecules orient approximately one hydrogen atom along each OO axis. That means you have OH, the hydrogen bond O. Under ordinary conditions, the interactions of non-adjacent molecules do not stabilize any one of the configurations that satisfy the conditions that we just discussed. Meaning to say that normally the molecules that are not next to each other don't have a role to play in the direction. That's what the not stabilizing non-adjacent molecules means. So the question is, if we have unconstrained orientation of a single hydrogen H2O molecule in tetrahedron, how many ways can we arrange it? By unconstrained, I mean that there is a tetrahedron and no one position is favored over another. How many ways can we arrange it? Think about it for a while. And I'm going to show you this, which you may have also come across in a physical chemistry textbook. It is nothing but a tetrahedron. So think of this as a three-dimensional geometry. I have drawn the dashed line to indicate it is in the third dimension, through the plane, below the plane of this screen that you're watching. And the water molecule, then, which has oxygen at all one, two, three, four vertices. So each vertex is the location of a neighboring oxygen, resulting in the fact that the hydrogens can be located at any of the vertices for the same charge issue. This is what the tetrahedron model looks like, the 1H model of Pauling. It also, however, means that it doesn't have to be in state 1, which I marked here. It could be in 2, 3, 4, 5, or 6. In other words, what I have done is I have picked each pair of neighboring vertices and installed my H2O according to that, giving me 6 possibilities.